In this section, we will discuss three measures of variation: the range, the variance, and the standard deviation. First, the range. The range is easy to compute. The range is always computed as the largest minus the smallest value. For this example, our largest value is 241. Our smallest value is 127. Therefore, our range is 241 minus 127, which is 114. For this data set, our range would be our largest value, which is 615, minus our smallest value, which is 425. Therefore, our range is 190. Two additional symbols that we will see throughout this course are S squared, which represents the sample variance, and sigma squared, which represents the population variance. The sample variance is computed as the summation of the squared difference between each data value and the mean, divided by the total number of items in our sample minus 1. The population variance is computed as the summation of the squared difference between each data value and the population mean, divided by the total number of items in our population, which is capital N. These measures can be easily computed if we set up the proper table. The standard deviation. The standard deviation can always be computed as the square root of the variance. Two more symbols that we'll see throughout this course are S, which denotes the sample standard deviation, which is computed as the square root of the sample variance, and sigma, which is the population standard deviation, which is computed as the square root of the population variance. Let's explore this example for our sample of 5 football player weights. In order to compute the variance and the standard deviation, you should begin by computing the mean of your data values. The mean of our data values, as computed previously, is 277.4. We should then set up a table with the following columns. The first column should be XI, and in that column we should place all of our data values. The next column, we should record our sample mean value for all of our data values down this entire column. The same value, our sample mean, should be recorded down the entire column. In the third column, we should record the difference between each data value and the sample mean. And in our last column, we should square the difference between each data value and the sample mean. We should start by placing all of our data values in the first column. Then we record our sample mean value down the second column. In our third column, we should record the difference between each sample data value and the mean. In this first row, we take the difference between 255 and 277.4 and record that value here. In the next row, we do the same for the data value in that row. 216 minus 277.4 is equal to negative 61.4. In the next row, 346 minus 277.4 is equal to 68.6. We do the same for the remaining two data values. In our third column, we should square the difference from our preceding column. 22.4 squared is equal to 501.76. Negative 61.4 squared is equal to 3,769.96. 68.6 squared is equal to 4705.97. We do the same for the remaining two values in our chart. Next, we should sum the last column in order to get the numerator for our sample variance. The denominator is n minus 1. Since we have n equals 5 data values, our denominator is 4. Therefore, our variance is 2,385.8. We obtain the standard deviation by taking the square root of the variance and get 48.84. If these data values represented population data instead of sample data, our process would have been very similar. We would have set up a table, putting all of our xi values in the first column. In the second column, we would have called it our population mean, but the value would have been identical. In the third column, we still would have taken the difference between the xi values and the population mean to get the same values for our third column. In the last column, we still would have summed up all of our values. For the population variance, the numerator is still the sum of the last column. However, the denominator is capital N. Since we have n equals 5 data values, our denominator would have been 5. So our population variance is 1,908.64. We obtain the population standard deviation by taking the square root of the variance and get 43.69. Let's look at another example. Here, we want to compute the standard deviation for this data. We start by copying all of our xi data values in the first column. We then compute our mean and copy it down every row in the second column. In the third column, we take the difference between each xi value and the mean and record it here in the third column. In the fourth column, we simply square the value that we got in the third column when we took our difference. 1 squared is 1, 2 squared is 4, negative 2 squared is 4, and we continue down that column. Now we sum up the last column to get 50, and that's the numerator for our sample variance, and we divide by n equals 5 minus 1. Doing this, we obtain a sample variance of 12.5. and a sample standard deviation of 3.54. Now, let's get some hands-on practice. For this data set, let's compute the range and then the standard deviation. You should pause the video at this time in order to compute these measures. When you computed the range, you should have taken the difference between the largest value in our data set, which is 92, and the smallest value in our data set, which is 48. This difference is 44. Therefore, our range is 44. When computing your sample standard deviation, you should have completed a chart that looks like the chart presented on this slide. Your sample variance should have been 216.857, and your sample standard deviation should have been 14.73.